Good day, everyone. So in today's class, we'll be looking at the topic circular motion. At the end of this lesson, we'll be able to define circular motion. We'll also be able to define the terms associated with circular motion. And lastly, we are going to be solving problems involving circular motion. So let's dive into this. So what is circular motion? By definition, circular motion occurs when an object moves along a circular path around a fixed center. It is governed by a centripetal force that continuously pulls the object towards the center, preventing it from flying off in a straight line. So in a circular motion, there is an important force that is involved that makes it work, and that force is called the centripetal force. This circle can be vertical circle or horizontal circle. But whatever the kind of circle it may be, we experience a centripetal force that always keeps the object toward the center so that it does not go out of the track of the circle. In real world application, we could find circular motion in vehicles that are moving around curves. We can also see it in the movement of moon, around the sun and other planets too as well. So all of these are simple application of circular motion. All right. So I will say that let us now look at the terms that are involved in circular motion. We have the angular speed and we have the angular velocity. Sometimes these two terms are taken to be the same or they are a little different. Why angular velocity is vector quantity, angular speed is a scalar quantity because that's only magnitude and direction. By symbol, we use a symbol called omega that have an appearance of W. Some people call it W, but actually in a real sense, it's a Greek symbol. So this W or omega is a symbol that is used to represent either angular speed or angular velocity. And by formula, angular speed is angle over time, while angular velocity is angular displacement over time. So by definition, we say that angular speed is the rate of change of angle over time, while that of angular velocity is the rate of change of angular displacement over time, as you can see in the formula. The triangle you see beside the theta there represents change in angle over change in time. They have the same unit as well. The unit for angular speed and angular velocity is radian per second. By symbol, it is pronounced rad per second. As you can see here, this is the unit for angular speed or angular velocity. They are both rad per second. So, like we said earlier, there's a force that keeps an object in a circular path. That force is called centripetal force. Now, centripetal force acts on that object in a way that it directs that object toward the center of the circle. By formula, it is mv squared over r, where the m represents the mass of the object is directing toward the center, the v is the velocity of the same object, and the r is the radius of the circle. The unit of this force still remain Newton. Or the other unit can be kilogram meter per second squared. Now, let us look at an example on this. Look at the question 1 here. It says the force required to make an object of mass m traveling with velocity v turn in a circle of radius r is a mv squared over r, b mr squared over v, c mr over v, d mv over r squared, e mv over r. So of course, this is describing a centripetal force. It is the force that makes an object to turn in a circle, and the formula for it is mv squared over r. But permit me to mention that that is not the only formula for centripetal force. It has other formulas. Okay, so let me quickly introduce those formulas. It has other two formulas too, aside from the one we mentioned. We've been able to say that one of the formula for centripetal force is centripetal force itself, Fc. We have said that Fc is equal to mv squared over r. This is one formula. Another formula for centripetal force is also m omega square r. And the last one, centripetal force can also be ma. So aside from this, we also have this one, we have this one. Okay. Now, another question here says that the force responsible for holding the moon in its orbit around the earth against the gravitational pull of the earth is what? Centrifugal. No. In actual sense, centrifugal force is the opposite of centripetal force. While centripetal force is always drawing the body toward the center of the circle, centrifugal does the opposite. It draws it away from the center. So we are looking at centripetal again because it keeps an object in a circular form, in a circular path. So the correct option is D. It's not, it is not reaction. Reaction is another force on its own. Rotational force, no. It will have a rotational force if it is rotational motion, okay, but this is circular motion. So the correct option is D, centripetal force. There is nothing like tractional force, okay. So let's see another question again. Here it said a particle moves in a circular orbit of radius 0.0 meters. If the speed of the particle is 0.88 meter per second, calculate its frequency in circle per second. All right. So let's go back to the question again. A particle moves in a circular orbit of radius 0.02 meters. So we are given radius here to be 0.02 meters, right? If the speed of the particle is this, we are given speed, which we represent with letter V, to be 0.88 meter per second, right? Calculate its frequency. So you are looking for F, okay? But to find F, frequency. Now, how do we calculate frequency? So we've already established that one of the formula for angular frequency is change in angle over time. But permit me to tell you that this is not the only formula for angular frequency. Angular frequency has about 7 to 8 formulas. Now, if you are going to look at this, you're not going to solve all the problem you want to solve. In this case, you have to find frequency. Now, the one that relates angular frequency with frequency, this angular speed sometimes called angular frequency. So the formula that link this angular speed with normal frequency is omega is equal to 2 pi f. So how do we get frequency here? So you cannot get frequency directly. We need to get this angular frequency, and from there we will now able to get our linear frequency. So going by the, we also have another formula for angular frequency, which is V over R. Take note of this as well. So this is one, another one, another one. This is called angular velocity or angular speed. Sometimes you also call it angular frequency. Please take note of that. But the F here is linear frequency, and that's what we have to find. So now, in the parameter given, we are given R and V. So to get our angular speed, we'll use this. So omega, that is equal to V is 0.88, 0.88 over our R is 0.02, right? So that will give us, if we get a calculator to calculate that, 0.88 divided by 0.02, that gives us 44. So we have our angular speed or angular velocity or angular frequency to be 44 radian per second. But then we are not to find angular speed, but to find frequency. This will help us to find it. So from here, if you make F subject the formula, our F there will be angular speed over 2 pi, right? From here. So we've gotten our angular speed to be 44. So 44 over 2 times pi is 3.142. 22 over 7, approximately 3.142. So 3.142. So that will be equal to 44 over. Now, let us multiply, let's multiply 2 by 3.142. 2 times 3.142, and that is giving us 6.284. So we have here 6.284. So finally, let us now do 44 divided by 6.284. So 44 divided by 6.284. That is giving us 7, approximately 7. So our frequency is 7 cycles per second. Okay, so that's the answer. Now that is going to be option B. All right, I hope that is clear. So moving forward, we have another question here. It says a ball attached to one end of a string moves anticlockwise around a circle whose center is O. If the string suddenly breaks when the ball is at point P, along which of the following path will it move? Is it option A or option B or option C, option D? Now let us critically look at the question a second time. So a ball attached to one end of a string. Let us draw the ball. This is the ball, and this is the string attached to it. The ball is attached to one end, this is the second end. Now, moves anticlockwise around a circle. Now, let's say this ball is moving around the circle like that. Keep moving like that around the circle. Okay. If the string suddenly breaks when the ball is at point P, now maybe when the ball now moves here, the ball, okay, anticlockwise means that the ball is moving in this direction, right? This is clockwise direction, while this is anti-clockwise. Okay. Now if the ball now moves maybe to this point, and that's point P, still with the string attached to it. Okay. So the question now is, which part will the ball move if the string cuts? Okay. If the string suddenly breaks, which part will this ball now move? Of course, if the string breaks, definitely the ball will not move in a circular path again. It will move away from the path. So it will move at tangent to the circle. So it will move this way. The ball will suddenly move to that direction. So looking at option A, no, the ball will not move like this. It will move at tangent, okay, to the circle. Option B is correct. So once the string breaks, the ball will move tangent to the circle. It's not going to be C, it's not going to be D. The correct option is B. All right. Now let us see another question here. So here we are given a particle of mass 10 kilogram. So we have the mass to be 10 kilogram. Okay. It's fixed to the tip of a fan blade, which rotates at an angular speed of 100 meters per second. So we have angular speed, that is our omega, to be 100 rad per second, right? If the radius of the blade is 0.2, so we have R to be 0.2 meters. The centripetal force is, so we have to find centripetal force, that our Fc, unknown. Is it option A 2 Newton, option B 20 Newton, option C 200 Newton, and option D 400 Newton? Now, the best formula to use for this centripetal force is m omega square r. Okay, this is one of the formula for centripetal force, aside from the one of mv square r. So before you choose the formula, you must know that in that formula, all the parameters given must be available there. Only one should be unknown. In this case, we have to find Fc. So the m is there, Omega is given, R is given, so this is the best one. So our M is 10 times our omega is 100 squared, then times our R is 0.2. Okay, now 0.2 means 1 over 5. So this is 10 times 100 squared times 1 over 5, right? So 5 here 1, 5 here is 2. Okay, so that is 2 times 10,000, because 100 squared is 10,000, right? And that will be giving us 20. That will be giving us 20,000. Okay, 20,000 Newton. All right. So looking at the option here, I think there's a mix of none of them is correct. All right. So that's the solution to that question. Let us take one more question. Look at this question here. It said a particle in circular motion perform 30 oscillation in 6 seconds. Okay, its angular velocity is what? So we have to find angular velocity, is unknown. Perform 30 oscillation, that means our n, number of oscillation now is 30. Then the time it took it is 6 seconds. We have to find this. So another formula for angular velocity is 2 pi n over t. So take note of that too. So that is 2 times pi is 3.142. So 3.142 times our n is 30 over t, which is 6. Okay, so 6 here is 1. 6 in 30 is 5. So we can see here that 2 times 5, this 2 times this 5 is 10. So we have 10 times 3.142. But then if you look at the option, we are given, the pi is not converted. So instead of changing the pi to 3.142, so we will just substitute this value of pi and return pi back. Okay, and that will be giving us 10 pi. Okay, 3.142 represents pi. So our answer is 10 pi. That's option A, 10 pi radian per second. B is 5 pi radian per second, C is 6 pi radian per second, and D is 5 pi radian per second. So the correct option is option A, 10 pi radian per second. All right. So another question again. It said a boy timed 30 oscillation of a certain pendulum thrice and obtained the following. Okay, obtain the following: 1 minute 10 seconds, 1 minute 12 seconds. The first one is 1 minute 10 seconds. Second one is 1 minute 12 seconds. Third one is 1 minute 7 seconds, respectively. So the mean period of oscillation of the pendulum is what? Okay, that's the question. Now, I will leave this to you as an assignment to practice. How do we solve this problem? All right. So we are going to be doing the curtain here today. Thank you for listening and have a wonderful day. Bye for now.